Hello, everyone. We've had a request for um, a demonstration of problem number 6 from the homework, so here it is. This is what the problem, or this is what my version of the problem looks like. I'm sure yours is pretty much the same. It's going to be about systolic blood pressure levels. Okay. And it's saying that if the blood pressure level is above 120, then it's considered to be high. Okay. We have a sample of 100 measurements. And it's listed in the accompanying data set. So that's right here. Here's my 100 measurements. They've told me that the mean, the sample mean of that 100 item sample is 132.82, or I'm sorry, 123.82. So that's what X bar is. X bar is 123.82. It's the average blood pressure of my 100 people. So N is 100. And the standard deviation is that crazy number, 16.62865. So we have 16.62865. All right. Okay, so we've got the we've got this 3 pieces of data written down. And now they want, let's see what they're asking us for. It says use a 0.01 significance level. That means that our alpha is 0.01. Use a 0.01 significance level to do what? To test the claim that the sample is from a population with a mean greater than 120. All right, so this tells me that my initial hypothesis, it's always a statement about equality, so it'll be equal, mu equal to 120, and then the alternate is that mu is greater than 120. So this is the first part of the question. This is the solution to the first part of the question. I guess I'll go ahead and type that in. This will be mu equal to 120, and then mu greater than 120. Now they want the test statistic. Okay. So I'm going to do this in 2 ways. I'm going to do it with the formula, because you need to know how to do it with the formula. And then I'm going to do it with StatCrunch, because in the future you will probably end up using technology anyways. And but just like they got calculators, doesn't mean we don't need to know how to add stuff together by hand. So the test statistic is kind of like a z-score. Remember that a z-score was the observed minus the mean over the standard deviation. This is kind of like that. It's still an observed minus a mean over the standard error. The standard error. And the standard error here is just s over the square root of n. That's the standard error. And that's in the denominator. And the numerator is the observation, we observe this in our sample minus the mean, the population mean. So this is a test statistic. Well, then I have everything I need to compute that. X bar is 123.82, and the mean is listed right in the statement of the problem. You know, it's 120. That's what we're assuming the mean is. So that's a 120. And then down here in the bottom, these parentheses are important. Okay? It's this number, whatever that number is, s divided by the square root of n, that's the number that goes in the denominator. So make sure you are including those parentheses, otherwise you will have an error. So this would be 16.62865 divided by the square root of 100. $16.62865 divided by the square root of 100. Now the square root of 100 is 10. Right? So that number that's in the denominator is really 1.662865. And in the numerator, it's 120 something minus just 120. So you're just left with the 3.82 in the numerator. Then this is what I should calculate: 3.82 divided by 1.662865. And I get 2.297. But they want me to round to 2 decimal places. So my 2.297 would become 2.30. Now they want me to identify the p-value. Okay, well, this is the t-curve. Looks like the normal curve, but it also has the degrees of freedom. Okay. You get t-values down here on the horizontal axis, just like the normal curve had z-values. And we have a test statistic of 2.30. Zero's here in the middle, so 2.30 is over here somewhere. Okay, so that dot is 2.30. And we are curious about the area in the tail past the test statistic. This is what we are curious about. We have to compute the degrees of freedom, but that's easy to compute. Here it's just n minus 1. So we'll use a degrees of freedom of 99. Also, since this is a one-tailed test, specifically because of this greater than, it's a right tail, then this area is my p-value. So the area is the p-value. To get that area, I'll just go to StatCrunch. So you can click Get More Help, StatCrunch. your StatCrunch window opens. You'd go to Stat, Calculators, T. All right, here's my T calculator. We already said my degrees of freedom was 99 because that's 100 minus 1. And I would like to know what the area is past 2.30. It says the area is 0.01177. So that's this area. And they're going to have me round it to 3 decimal places. So we would get 0.012. State the conclusion. Students often find that this conclusion is the hardest part, but once you know the drill, it's super easy. The key is properly interpreting the p-value. The p-value is the probability The p-value is the probability that you will be wrong if you reject. The p-value is the probability that you will be wrong if you reject. Nobody likes to be wrong. If you disagree, then you're wrong. You should think more carefully about that. I promise that you don't like to be wrong. Who likes to be wrong? No one. We like to get things correct. So if I get my p-value, if I get my p-value and it says that, it says like 0.65, then that means there's a 65% chance of being wrong. Well, I can't tolerate being wrong 65% of the time. So if this was my p-value, I would not go out on a limb and reject that null hypothesis. However, if my p-value was something really small, like 0.02, then there'd be a 2% chance of being wrong if I reject. Well, that seems acceptable, 2%. We're just not sure if 2% is really low enough, because what if we really clamped down and said that we want a very strict limitation on the risk that we will take to be wrong? That's what alpha is. It says here that alpha is 0.01, that's 1%. That means that you can risk no more than a 1% chance of being wrong if you reject. Well, we found that our p-value was 0.012. Our p-value is 0.012. That's bigger than 0.01. So even though 0.012 is small, it's a 1.2% chance of being wrong if we reject. That's over 1%, so we will need to fail to reject. We will fail to reject. Anytime you fail to reject, the same thing happens. If I fail to reject, then that means there is insufficient evidence. Where is the evidence? The evidence is the 100 blood pressures that we measured from our sample. Fail to reject, insufficient evidence. If I had rejected, well then I would have sufficient evidence, because rejecting means that my probability of being wrong is low, so consequently the evidence is strong. In either case, this evidence is telling you about your ability to support the alternate hypothesis. Supporting the alternate hypothesis is synonymous with throwing the initial hypothesis in the garbage can. They mean the same thing. If the initial hypothesis is in the garbage can, then I got to have something, so I must be supporting H1. This is your flowchart. Coming up with that conclusion is no more difficult than interpreting this flowchart. Look, if I had failed to reject, then I would have insufficient evidence to throw the initial hypothesis away. But if I reject, then I have sufficient evidence to throw the initial hypothesis away. And throwing the initial hypothesis away means the same thing as supporting the alternate. So there is not sufficient evidence at this significance level to, and we got to read what they're talking about here. Do they talk to me about the initial or the alternate? Well, here, this is the alternate. This is the alternate hypothesis. Blood pressure level greater than 120, that's the alternate. We do not have enough evidence to support the alternate. Now, I said I was going to do this in two ways, so let me show you what StatCrunch will do for us. So if I go to T-Stats, one sample with summary, then I can get this window, this dialog box, and it is wanting to know the very information that I used in the problem to get my calculations. The sample mean was 123.82. The sample standard deviation was 16.62865, and the sample size was 100. I'm doing a hypothesis test to check if mu is equal to 120 or if mu is greater than 120. I hit compute. It gives me this result. It tells me what my sample mean was. Okay, I already knew that. It tells me my standard error. Well, that was my denominator of the test statistic. It tells me the DF. We knew that was 99. Here's the test statistic that they compute, 2.116. So that's a little bit off from the test statistic that I got. I wonder why. Let me look again. I can go to options, edit. 1.2352. Oh, that's why. It should be 1.2382. Now they have a test statistic of 2.297. Well, that's exactly what I had got, 2.297. And their p-value was 0.0119. And that is naturally going to be a little off from what I had, because when they calculated their p-value, they did so with the test statistic 2.29724. So they didn't do any rounding. Their test statistic was 2.29724. So it was a little bit this way. It gave them a little bit more area than 0.0117. So the area that they got was 0.0119. I mean, it's different by 2 at the 4th decimal place. That's very small. And the question still would have accepted that answer. No problem. It would have rounded to the same thing anyways. So, all right, that's it. Talk to you later.